Hi, I'm Tim, and this is the fifth in the series of Antigravity Matter videos. This one is actually the first of three that deal with spiral galaxies. This video is only an overview. If you want more detail, see the Antigravity Matter document linked to the website. In a spiral galaxy disk, there is antigravity matter in the interstellar space between the stars in the disk. As the stars orbit, they push through the antigravity matter, and they're affected by drag. But the reaction force acts on the antigravity matter and causes it to rotate. This means it gets flung outwards by the rotation of the disk. But that creates a reduction in density of antigravity matter near the centre, a lacuna, and that attracts antigravity matter and gives the antigravity matter a centripetal acceleration. That means it follows a spiral path as it flows outwards. The orbits of the stars in the disk decay and the stars gradually move inwards. But the antigravity matter drag also acts on molecular clouds and other molecular matter, and it acts more strongly on them because they're much less dense, so it blows them outwards. And you get this kind of flow in the disk. Stars are moving inwards and molecular clouds are going outwards. As they go outwards, they coalesce and grow and cool and form more stars. And that's why star formation tends to happen in the outer reaches of a galaxy disk and not so much in the inner disk. Nevertheless, despite all this movement, the net flow of matter is inwards. And here are a couple of examples that demonstrate that. Bottom middle, we have a small galaxy that clearly has a dark ring around the outside of the luminous galaxy. This is molecular matter that's been blown outwards by the antigravity matter in the disk. We just happen to be able to see it because it's silhouetted in front of the larger galaxy in the background. And top right, the pink is molecular matter that's been blown out by the rotating galaxy. And this image demonstrates that the flow pattern actually extends a long way out beyond the edge of the visible galaxy disk. The flow pattern of antigravity matter in a galaxy is complex, and I'm going to describe it in a series of stages, and I'm going to build up the diagram in a series of steps. But these aren't the steps of the development of a galaxy. These are just steps of me developing the diagram. And we start with the galaxy disk. What I'm showing here is just the antigravity matter. So the grey is the antigravity matter of deep space, and the white spots are the AGM lacunas around each of the stars in the galaxy disk. As the star's orbits decay, the galaxy gets denser in the centre, and eventually the stars in the centre get sufficiently dense that they develop a shared AGM boundary around a large region of the core. The stars inside the shared AGM boundary are at their AGM exclusion density. There's no antigravity matter inside the shared AGM boundary, so the stars there don't feel drag. So they retain their energy and they move chaotically, interacting with each other, falling inwards, flying outwards. Some of the stars that fly outwards manage to pass through the shared AGM boundary, and then they get into the outer core where they're pushing through the antigravity matter, they're affected by drag, and most of them eventually fall back again into the inner core. So the stars in the disk are orbiting the galaxy in an approximately circular manner, and the stars in the core are moving chaotically, and a lot of their movement is in and out. As time passes, more stars fall into the core from the disk and they deliver energy and angular momentum. The core gets bigger and more stars are ejected into the outer core where the energy and angular momentum is lost to AGM drag. The antigravity matter is flowing outwards in the disk, and that means that there's a reduction in density of antigravity matter in the region of the galaxy, an AGM lacuna. And I'm going to zoom out here. So the lacuna in the galaxy attracts antigravity matter, and the antigravity matter above and below the disk is attracted inwards. The antigravity matter that's a long way away from the system is probably very cold, But as the anti-gravity matter gets sucked into the disk, it's heated by interaction with the passing stars, and it can get to many thousands of degrees. But as the anti-gravity matter flows out through the disk, it cools. A circulation develops where the anti-gravity matter that's flung outwards by the disk circulates round and re-enters the galaxy along the axes. The anti-gravity matter that's coming in along the axis has some angular momentum because it's been ejected by the disk. So as it comes in closer to the axis, it rotates faster, and this generates an AGM lacuna. So the AGM lacuna of the galaxy extends away from the plane of the disk along the axes. And of course, this is a dynamic AGM lacuna, so an antihalo develops around the outside of the system. This is a region of slightly increased anti-gravity matter density. And here's a plot of the density of anti-gravity matter in interstellar space across the system. In the centre, we have an AGM boundary around the inner core, and no anti-gravity matter within that. Outside that, you have the shape of anti-gravity matter density profile that you might expect from a vortex. And outside that, you have the antihalo, where the anti-gravity matter density is slightly increased. Not included on this plot are the AGM lacunas of individual stars in the disk. A normal matter particle that is situated at the outer edge of the galaxy disk is attracted inwards by a gravitational attraction to the other normal matter objects in the galaxy, and by an attraction to the static AGM lacunas of the other normal matter objects in the galaxy, including the shared one in the centre, and it's attracted inwards to the dynamic AGM lacuna caused by the rotation of the galaxy. The dynamic AGM lacuna only involves a relatively small reduction in density of anti-gravity matter, but the volume is enormous, so it often has the strongest effect on the galaxy. A normal matter object that was outside the antihalo would only be attracted to the normal matter and the static lacunas of the galaxy. The effect of the dynamic lacuna would be cancelled out by the effect of the antihalo. Now, what happens if two galaxies are rotating in the same direction and arranged approximately on the same axis? Well, the two vortices extend along the centre line and they meet up, and they generate a linear AGM lacuna that stretches from one galaxy core to the next. That lacuna attracts normal matter objects and captures stars. And here we have, on the left, two galaxies that are in that situation. Their vortices have extended and connected up. An AGM lacuna has developed between the two galaxy cores, and that has captured this string of stars. That's likely to be a temporary feature that only survives as long as these two galaxies are aligned. As they move out of the alignment, the two vortices will break, the string of stars will break, and the stars will fall back into one or other of the galaxies. And that appears to be what's happening to the galaxy on the right. So I haven't added any new terminology, and I'm going to end this video at that point.